This is the Nomad Futurist podcast, a podcast about the evolution of technology, society, and transformation. Connect with us, share your thoughts with us at nomadfuturist.com. Let's get this started. Here are Phil and Nabil.
Howdy, it's Vint.
Well, Vint, thank you very much for taking the time to join us.
For those listeners that don't know, Dr. Vint Cerf is the godfather of the internet, the inventor of the internet.
No. Look, let's get this straight. It's true that Bob Kahn and I did the original design work in 1973, but literally millions of people have contributed to this over the years. It wouldn't be the scale, scope, and success without all of those contributions. So I don't want to take.
Well, for those of our listeners that think Al Gore invented the internet,
actually, he helped.
He helped. There's no question he helped.
He absolutely did on the legislative side. And we're very grateful for that because he broke some barriers and helped to facilitate things to happen that might not otherwise have happened. And so it's a very substantive contribution.
Well, as someone who has spent my entire adult life in the critical infrastructure industry, I would have had nothing to do. I would be destitute if not for the little idea that you guys came up with. So thank you.
Sometimes good ideas are good ideas.
Could you expand a little bit about how you got into space and lessons learned?
Well, first of all, I got introduced to computers at a relatively early age for the time that it happened. My first exposure was in 1958 to the semi-automated ground environment system, which was a radar system that was taking radar material from the distant early warning radars in the northern part of Canada over telephone circuits to a system that was trying to detect and figure out automatically whether there were Russian bombers coming over the pole. And so this was a tube-based system. So you literally walked into the computer in order to use it because the tubes were lining the walls. It was pretty amazing. This was 1958, so I am all of 15 years old at the time. 2 years later, I got an opportunity to actually work on a computer and write some software at UCLA, even while I was still a high school student at Van Nuys High. So computing really grabbed my attention in my early teen years. Then I went to Stanford to do undergraduate work in mathematics, but I took every programming class that I could. And then I went to work for IBM. And then after 2 years in Los Angeles, and after 2 years, I realized I really needed to go back to school to get a more deep founding in a fundamental understanding of operating system design, hardware, and programming languages, and computational theory and things like that. So I went to UCLA and joined the PhD program. And in the middle of all that, the Defense Department started the ARPANET project. And I got drawn into that because one of my thesis advisors or on the thesis committee was Len Kleinrock, who was an expert on queuing theory, who was using that theory and his dissertation work at MIT to model the way packet switch networks would function. And so we used that theoretical basis to analyze how the network or predict how the network would work. And then my job was to actually run experiments on the network, gather the data, and compare the data we gathered with the predictions that these things would make. And while I was doing that, I met Bob Kahn, who was one of the architects of the ARPANET. And we sort of bonded instantly and worked together on the analytics side of things. And later, when I went up to Stanford after I finished my PhD, Bob came out to my lab and said, this ARPANET thing really works. Now we're interested in using computers for command and control. But that means we're having to put computers in mobile vehicles and in aircraft and ships at sea. We can't use telephone circuits to do that. So he started working on mobile packet radio and packet satellite. And so we had three network technologies, all packet switched, but all very different in terms of packet lengths and data rates and error rates and latencies and so on. The question then was, how do you hook all that stuff together and make it look uniform? That's where TCP/IP came from. And the interesting thing is that a mile and a half from my lab was Xerox Palo Alto Research Center, where Bob Metcalf and David Boggs were working on the Ethernet, which is yet another packet switching technology derived from the AlohaNet project, another DARPA-sponsored project at the University of Hawaii, using essentially dynamic radio access to the University of Hawaii Computers. So I'm sorry, that's attempting to compress a whole lot of stuff in a short amount of time, but I got drawn into this inexorably. And once the internet design work got started, it has stayed central, frankly, in my career ever since.
Talk about being in the right place at the right time.
I think that's a very important thing to keep in mind. I mean, this isn't me personally. It's the fact that I happened to be there at the right place at the right time. Bob Kahn came to me and said, "Would you help me with this?" And so it was mostly luck that led to this. Although I remember having some meetings with some Nobel Prize physicists who were then asked by a student, did you know that you were going to get the Nobel Prize when you were doing this? And one of the physicists said, look, getting the Nobel Prize is 95% luck and 5% knowing how to do the math. And, a lot of that is applicable to the internet story as well.
I mean, to the extent that, there are lessons learned from that whole basis, do you think it's that you were open to those experiences and you were curious enough to, want to get involved in it as opposed to shying away from it and going on some predetermined path?
Actually, there are lessons, but they're much broader than what you just suggested. I mean, there were some personal lessons. For example, while I was at Stanford, I was working very hard on the TCP protocol. Later, we split into TCP/IP. And ARPA asked if I would invited me to come and run the whole program, the internet program, packet radio, packet satellite, packet security, and everything else. And I said no. Because at the time I thought, well, it's going to be a big deal. It'll be very visible. If I screw up, everybody will want me to bring up. So I said, no, I don't want to do that. And they wouldn't take no for an answer. And so I later looked back on that and realized that, when you're young, it's okay to take risks. It's not fatal if it doesn't work and, you have time to recover. So the big life lesson for me was, take risk while you're young because, that's when you can recover from failure. But there were other deep lessons in design and architecture that I took away from this. I'll give you capsule examples of this. The internet layer protocol, once it was defined, had three interesting properties. The first property is that the packets at that layer had no idea how they were being carried. That was a really good idea because then we didn't know or chose not to know anything about the details of the underlying transport. So Ethernet would work and mobile radio would work and packet satellite would work and eventually optical fiber would work because the transport details were unknown to the internet packets, and the packets were routed independent of the detailed nature of the actual transport mechanism. So ignorance is your friend in that case. Same argument got made in the other direction. The packets had no idea what they were carrying. They were carrying a little bag of bits from point A to point B, but they didn't know what they meant, which meant that the only thing that cared about what those packets meant was the software at the edges of the net. And so this notion of end-to-end communication, transparency end-to-end through the internet, meant that when new applications came along, the network didn't change. You had no idea what the applications were.
So ignorance is bliss.
Yes, exactly. So it meant when new applications came along, the network didn't have to change because it didn't care what the bits meant. The only thing that cared was the software at the edges. So these were really fundamental ideas that were part of the system. Another good example, if you look at the internet protocol specification, it doesn't say anything about routing. And of course, we all understand that routing is sort of fundamental. You hand a packet into the net. If you don't know how to route, it doesn't go anywhere. So that was a really important thing, but we left it out of the internet protocol because we said we didn't know how to do it. But we said, but there will be a table. And the table will have some, things in it where you look, where is this going? And you look it up in the table and it says, send it over there. Then we said, okay, somebody has to figure out how to populate the table. And we explored a whole bunch of different routing algorithms to find ones that worked and some that didn't. So this idea of incompleteness and deliberate ignorance is sometimes your friend when you want to build something whose certainty is uncertain and whose design is open. That's the other openness thing that I will cite here in this long peroration is that we were open to new protocols being added horizontally. So you have file transfer protocol and you have the simple message transport protocol and you have hypertext transport protocol. All these things relying on top of TCP. and TCP was sitting on top of IP. But next to TCP was UDP, the User Datagram Protocol, which was used for real-time communications of the kind like we're doing right now with real-time packet radio or packet video and packet audio. So this extensibility, this willingness to let people invent new things and fit them into the architecture that was not so rigid that it would reject that, was really powerful, because it meant when the system had the capability to support something new, like streaming video, you could add it to the system and it didn't break the architecture.
So architecturally speaking, do you think we are ready for the qubits bringing quantum computing into communication? I mean, are there any security concerns and lessons that we should actually start thinking about? And how much data is the existing infrastructure ready to support?
Well, first, several issues here. The first one is that transporting an entangled photon is a non-trivial exercise. Getting it to go over a fiber is the easy part. Getting it to go far enough so that you could build an arbitrarily large multi-quantum computer network, a network of quantum computers, is much harder, because at some point you have to do a relay of the entangled photons. And that is the hard part, figuring out how do you essentially destroy the incoming photon, but capture its state so that it could be replicated in a new photon that goes further on its way, hopping through the quantum network. That's hard. Nobody has figured out exactly how to do that. The other thing that's important to know is that quantum key distribution is a separate thing from quantum relay. Quantum key distribution simply means that if someone is attempting to intercept the distribution of keys, the distribution of any particular intercepted bit will fail. And that doesn't mean that you know that somebody's out there. All you know is that some bit didn't make it. And so it makes it, if you successfully get the keys distributed, then you can verify that both sides got the same key. That's really, and I don't want to trivialize that, but that's really what quantum key distribution is about. And that's different from doing quantum relay. We still don't really have any quantum computers that do anything useful. We at Google, we spend time and have done very successful implementations of increasingly large quantum computers, but the only thing we demonstrated was something called quantum supremacy, which just meant we could do a computation that could not have been done by conventional means in less than a few thousand years, whereas we did it in a few minutes, which demonstrated the utility of the quantum computation, but it didn't actually perform a function that was useful, like an optimization or a traveling salesman problem solution in 2 milliseconds and things like that. So we're still waiting for the quantum world to catch up with some people's aspirations.
Well, it allows the marketing folks to say that Google has achieved quantum supremacy.
Well, yes, it's a terrible term because it's misunderstood in many cases. The thing I'm looking for and have predicted is that in this calendar year, 2021, we may see at least one useful computation coming out of a quantum computer, something that is of pragmatic value. And of course, it'll be easy to test whether that prediction works, because about this time in 2022, we'll know whether that's true or not.
I think I can say for myself, and I'm going to speak to all of my guests, and hopefully I don't insult anyone, that everybody that we've spoken to that, claim to be experts in our space has been faking it. I mean, this is clearly, the level of understanding at the fundamental level simply doesn't exist with this generation. And in large part, it's just, you were there when it started. So all of the pieces are so fundamental to you, in the same way that, when I'm explaining to someone how to turn on a computer because I've been using them my whole life, that to me is, it's muscle memory. It's nothing that is like a knowledge base that I can take a test on. But it's breathtaking. It really is. I don't want to embarrass you on it, but it's unbelievable.
Well, it's been 50 years and my memory hasn't totally dissipated, fortunately. So this whole thing is in many ways a personal experience for me. It's something I have lived through day by day, watching it grow. And some people look at this now and they say, holy crap, how could you possibly have imagined that? And the answer is, well, we didn't imagine everything. But what we did know is that what we were doing had this powerful enabling potential. And I would not have been so committed to internet and all the various institutions associated with it, like the Internet Society and the Internet Engineering Task Force and Internet Architecture Board and the Internet Corporation for Assigned Names and Numbers. I wouldn't be so committed to all of those things, except for the fact that I believed then and still believe this is powerful enabling capability. And we have many, many more things that we can do with it than we've already figured out how to do. And at the same time, recognizing how powerful this is, we've seen how much damage it can do in the wrong hands. And so when you see misinformation and disinformation and some of the kinds of things that we were talking about, before we officially opened the show about what's going on in Washington, D.C. right this moment, a lot of that is enabled, sadly, by the abuse of this same technology, which creates a megaphone and distributes information as well as misinformation with equal ease.
Based on the fact that you've spent a significant time in developing this, seen it, grown with it, what are some of the top predictions that you have as to where we are headed?
Well, it's very clear from the trend point of view that an increasing amount of computing at the edge of the network is happening. I don't want to confuse the term edge computing necessarily, so let me explain that for a moment. One thing clearly is that we've ended up bringing computers with us as opposed to going to them, and that's why we have smartphones and pads and laptops and things like that. We're also starting to see opportunities to take cloud computing, which is really time sharing on steroids, and interpose between the cloud computing resources and the edge devices that we would normally think of, like the Internet of Things and laptops and desktops, and interpose additional computing capability, which people call edge computing now, in order to reduce latency, for example, or to increase resilience by temporarily storing information, for example, or processing information locally and then sending summary information into the cloud. So we can see that trend happening. We can see increased bandwidths everywhere, whether it's over optical fiber, over radio links. We have 5G coming. We have people who are exploring successfully very, very high data rate systems operating at 65 to 95 or even more gigahertz. So way, way, way up in the high frequency spectrum. What about all the satellites that Elon Musk and Starlink are putting up, and others are, OneWeb and others are putting up satellites? Pretty soon it'll be hard to avoid access to the internet because, it'll be available everywhere. And then, of course, the thing that I get all excited about is the extension of the internet to operate across the solar system. And that's been going on since 1998. It's been portions of it have been in prototype operation since 2004 in Mars or at Mars, as well as now at the International Space Station. And it will also be in use, I'm reasonably confident, as we return to the moon in the mid-2020s. That's not using the TCP/IP protocols. We had to develop a new suite of protocols to deal with latency, very high and variable latency and disruption and so on, which TCP was not as well prepared to cope with. But the idea of being able to network the solar system so that manned and robotic exploration gets the kind of communication support that it needs is really cool. It's like living in a science fiction story. So that I will comfortably predict will unfold over the decades ahead, particularly as we send spacecraft out with scientific missions, whose platforms, whose robotic spacecraft can be repurposed as nodes of an interplanetary backbone. So you can sort of imagine growing this thing mission by mission, leaving behind equipment that gets repurposed, which is what we did, for example, on Mars. We took the orbiters that were used to map the surface of Mars and we reprogrammed to be nodes of an interplanetary relay system. So that's a very exciting possibility. And we haven't even touched on things like machine learning and where that's headed, also turning out to be extremely powerful technology, and there's more to come.
You should start a section of books, like novels, called Science Fact, because in some cases, science fact seems more exciting than science fiction.
It's truth is often stranger than fiction, and that's what makes science so much fun. I mean, you have no idea what you're going to uncover next, or what someone else is going to uncover, and it will lead you to explore spaces that you didn't know exist. Look at what we discovered now. We thought we understood the universe. Now we discover that 95% of it is a big mystery. We don't know what dark energy is. We don't know what dark matter is. And we do know and have a great model for about 5% of the universe. And the other 95%, we have a model for it all. And except for the fact that some of it shows gravity and maybe dark energy is causing the universe to expand. But we don't have any good theories about why that should be.
Yeah, maybe this is just the beginning. So Dr. Cerf, one of the messages that we have is for the younger generation to come into our space. We want to encourage the younger folks to take the bull by the horn, learn and develop and grow and pass on your legacy to those folks. What are some of the key drivers, key messages that you would like to share with the listeners?
Several. Okay. The first one is make friends and keep them. And the reason that's important is as you get older, your friends will end up in really powerful positions. Some of them will, and that'll be really cool. So hang on to your friends, build bridges, don't burn any bridges if you can avoid it. Second, if you're going to take risks, take it early. I mean, don't do stupid things like jumping off a building to see whether gravity still works. But the whole point here is that when you're young, you have plenty of time to recover from a mistake. And as long as you make mistakes that aren't fatal, most of the time they're important lessons to be learned from trying things out and discovering that they don't work. It's often the case that a failed scientific experiment, it teaches you more than a successful one does, especially if it turns out that the experiment disproves a prediction that your theory, your pet theory made. That's hard because you might have to give up this theory that you've been clutching to your chest for years. But if you're a good scientist, you will accept the idea that some experiments will essentially falsify a theory and then force you to figure out, well, if that theory isn't right, what is the right theory that accounts for the results that I'm seeing? So for young people, especially, don't be afraid to break out of the conventional thinking if that's merited, because much of what we discover turns out to be something that doesn't look like it's possible, or it gets rejected by the mainstream. And then sometimes many years later, it's realized that was an important insight. That's why a lot of people get the Nobel Prize, but sometimes a long time after the thing they did was discovered, because when they discovered it, everybody else said, no, it must be crazy. And then 30 years later, we say, wow, they were actually right, weren't they?
So are there any particular areas that you believe are good thing? And if so, what would those be for people to start putting more emphasis on?
Well, there are a bunch of them. I mean, the obvious one is astrophysics. People say, what should I do? And I say, go into astrophysics. We don't know anything about 95% of the universe. So anything you do will probably win a Nobel Prize. But I would say in biology in particular, our increased understanding of how life works is fascinating. I have a 1,700-page book called the Mycochemistry or Microbiology of the Cell. And when you look inside of a cell, you discover not a bag of water with some chemicals going in there, but something which is more complicated than downtown Manhattan. I mean, there is an unbelievable amount of stuff going on in there. It's all kind of organized. It's not total chaos, but it's very complicated. So microbiology and understanding life, I think, is extremely important. The second thing would be neural interfaces. My wife has 2 cochlear implants. That wouldn't work unless we understood how to connect electronics to the inside of her cochlea, to the auditory nerve. It works spectacularly well. She hears now after being deaf for 50 years. And so applying that knowledge now to optical repair of vision, or possibly a motor repair, where you have a spinal injury and you've lost the use of your legs or your arms. I anticipate that we will be able to relay those signals using neural interfaces to electronics. I think that's well underway. So on the biology side, I think that there's an enormous amount of work to be done and value to be created. And certainly the results of the COVID-19 response, where within a year, a number of different vaccines were invented, just tells you where we are right now. Another place that I think is ripe for exploration is understanding how to write software that doesn't have bugs. for the last 80 some odd years, we've been all writing software and it always has bugs. So the question is, how do you create a framework in which you can write software where the framework says, don't do that because that's a buffer overflow, or don't do that because you referred to a variable that you didn't set. So you're getting a random result. We have to have better programming environments, and that's an area of research which has been slow to mature, frankly. And in fact, mature is not the right word. We're barely at the beginning of understanding how to build a framework where our mistakes can be caught before they get out into the field. The Internet of Things, of course, is rapidly progressing, and that's a big area of potential. Internet of Medical Things is highlighted because of the COVID-19 situation, where we have to have remote visits to our doctors. So now we need instrumentation that we can have at home that's not too costly, that lets the doctor do a remote exam, in effect. This is sort of like the tricorder in Star Trek, except we need it in the 21st century, not in the 24th.
Again, science fact over science fiction, right? I like to shift gears just for a quick second. If you had to, looking back on how this thing that you had a handle in creating has materialized, in some cases for, unbelievable technological advancement. In other cases, like what we're seeing in some of our politics today, to the detriment of society in terms of amplification of
fake news.
Fake news. I hate that word, but is there anything that surprised you with how, the internet got adopted, with the timing, with any of that stuff? I mean, you were working on this stuff 50 years ago, and really the internet didn't come into its own until, the turn of the century. When we got to, 96, 97, 98, towards the 21st century. So surprises. What do you think?
Well, the biggest surprise, I think, was the arrival of the World Wide Web. Tim Berners-Lee announced that in late 1991. Not too many people noticed. A couple of guys at the National Center for Supercomputer Applications, Mark Andreessen and Eric Vina, built the Mosaic graphical interface browser version of the World Wide Web. And that was noticed by a lot of people. I want to say millions. I don't know what the right number is. But a lot of people downloaded the Mosaic version because it made the internet look like a magazine. Had formatted text and imagery and eventually streaming audio and video. That was a very important invention because it made it easier for people to share their information, which is what Tim was trying to do. The result of that, of course, was the rapid growth of web pages to the point where nobody could find anything. So you needed search engines. And so along comes Alta Vista and Yahoo and Google and Bing and others. Now that was a surprise. I had not anticipated that the consequences of rapid growth of content driving the need for search engines in order to find things in this huge ocean of information. Even though we knew about the idea of surfing the internet for information, we didn't have quite the same vision as Tim did of what the World Wide Web might look like. And I'm sure that there are probably some people hiding in, a dorm room somewhere who are coming up with another idea, which none of us have thought of, that will transform the internet once again. And that again comes back to this open architecture, this openness to new ideas and the instantiation of new protocols to support them. I will say, just to come back to one of your questions about life lessons, one of the most valuable ones that I've taken away from this experience is that patience and persistence really count. And it took a long time to get from the conceptual idea of the internet to the point where it was visibly having an impact. It took on the order of 20 to 25 years. And by the way, it took almost that long for the interplanetary system to get to the point where we can reliably anticipate that it will proliferate. It started in 1998, first prototypes to Mars in 2004. And of course, here it is, 2021. And we're just getting to the point where the standards are being adopted. NASA, ESA, JAXA, and the other space agencies are starting to take advantage of this for purposes of planning future missions. So patience and persistence are really important to keep in mind if you want to do something really big.
Thank you very much, Dr. Cerf, for taking the time to join us and sharing thought-provoking information and your history. I believe we are actually just at the chasm. We are just breaking into what's next. Tomorrow is the beginning, and it is today. Any last words you would like to share with our audience?
Well, only to encourage people to go and explore their ideas. Don't be afraid of thinking out of the box. Don't let somebody say, "Oh, the conventional wisdom is XYZ, so you should ignore that." If something catches your attention or if something doesn't quite seem quite right, you should go explore that, because who knows, you might discover the next internet.
It's been an absolute honor. Thank you so much.
Well, thanks very much for letting me join you. I really enjoyed it too. Cheers.
Cheers. This has been great. Nothing lasts forever. Markets will come back, currencies will rebound, businesses will go on, and we'll all move on. That could happen next week, next month, or next year. I'm confident that those who prepare rather than panic will come out of this stronger. Thank you for joining us. This has been brought to you by Nomad Futurist. Check us online at nomadfuturist.com.